Morning students. So our next discussion on Millikan's oil drop experiment. In J.J. Thomson method, we found the EBM ratio of electron such as 1.76 into 10 power 11 coulomb per kg approximately. That is from the J.J. Thomson method, J.J. Thomson experiment. From this Millikan's oil drop experiment, we are going to estimate the charge of electron such as 1.6 into 10 power minus 19 coulombs. From these two expressions, we can estimate the mass of electron. How? The charge of electron per E/M ratio of electron. That leads to the value as 9.1 into 10 power minus 31 kg. That's it. So, ఒక వ్యక్తి ఏమో మనకి ఒక సైంటిస్ట్ ఏమో స్పెసిఫిక్ ఛార్జ్ ఆఫ్ ఎలక్ట్రాన్ ఫైండ్ అవుట్ చేయడానికి చెప్పారు. ఇంకొకళ్ళేమో ఛార్జ్ ఆఫ్ ఎలక్ట్రాన్ ఎలా మెజర్ చేయొచ్చు అని చెప్పేసి. సో ద Millikan's oil drop experiment. సో ఈ Millikan's oil drop experiment మనకి ఇంకా పూర్తిగా అర్థం కావాలి అనుకుంటే మనం ఈ ఎక్స్పెరిమెంట్ చేస్తున్నప్పుడు 4 కైండ్స్ ఆఫ్ ఫోర్సెస్ని మనం తీసుకుంటాం. ఏమిటా ఫోర్సెస్ అంటే I'll do the diagram regarding representing that Millikan's oil drop experiment, but before that we have to study, we have to learn, we have to remember the equations for the different forces. So the basic forces he considered for this experiment is gravitational force, buoyancy force, electric force, viscous force. First వీటి యొక్క బేసిక్ ఫార్ములాస్ రాసిన తర్వాత since force is a vector quantity, we must give the direction associated with that vector, in which direction the force is acting. Is there any conventional direction, any standard direction for the given force, or the force depends on the configuration we are choosing? Right? Okay. So first of all, I would like to write the right expression for the gravitational force. If m be the mass of the particle and c is the acceleration due to gravity, the gravitational force formula is mc. Since density is equals to mass upon volume, I can write this one as density into volume into z, where d is the density of the material I am choosing. Coming to the buoyancy force, the buoyancy force formula is also mc, but the buoyancy force is related to the fluid, the medium, in which medium it is moving. So even though the formula is same, I have to take the density of the medium in which the body itself is in motion. So here I am representing the density of the medium as d prime v z. Here the both v and v are the volumes of the material I am taking. Next, electrostatic force. If charge is the particle, q is the charge of the particle moving in the electric field intensity E, the force experienced by the particle is QE, where q is the charge of the particle, E is the field intensity. Next, and the last, viscous force. Viscous force. So there is a formula for the viscous force. Of course, you have to remember this formula. In mechanical properties of fluids, we studied about the surface tension and viscosity. There we have the expression for the viscous force as 6 pi eta or V. What are the words? What are the terms involved in this one? Eta is the coefficient of viscosity of the material we are choosing. R is the radius of the material we are choosing. V is the velocity of the particle we are choosing. This is also known as the Stokes formula, Stokes law, 6 pi eta RV. So these are the formulas where we are going to use this. Now coming to the directions, is there any specific direction for that force, or that force depends on the configuration we are choosing? That is what we have to see. So the gravitational force is always acting vertically downwards. It is always acting vertically downwards. Buoyancy force is always acting vertically upwards. Whatever be the motion of the particle in the medium, in the given medium, these two forces are in these kind of directions. One is acting vertically downwards, and one is acting vertically upwards. That's it. The electrostatic force depends on the nature of the charge and the field intensity we are applying. The electrostatic force depends on the nature of the charge, whether it is a positive charge, negative charge, or in which direction the field is applied. If the charge is Q, if the charge is Q and it is moving along the direction of the field intensity, the force is also in the same direction. If the charge is positive and it is moving along the direction of the field intensity, the force is also in the same direction. If charge is negative and the field is moving along the direction of the field intensity, the force is opposite. I can't say diagrammatically here. You can imagine something like this. See, this is the positive plate if I am seeing, and this is the negative plate. So the field intensity is always acting from positive terminal to the negative terminal. This is the direction of the field intensity. If I am placing a positive charge in between the two plates, then it is moving in the direction of the field intensity. Obviously, because this is the positive charge and this is the positive plate. So there is a repulsion between these two. So the force is acting along the direction of the E itself. F is in parallel with E if Q is positive. If the particle is negatively charged particle, then the F is acting opposite to the field direction. So the force depends on the nature of the charged particle, whereas the field intensity direction here. So here I am not able to give any specific direction in this one, right? That depends on the two things. Coming to that viscous force. So what is the direction of the viscous force? If the object is moving in the medium, like this, it is moving vertically downwards, the viscous force is acting upwards. If the object is moving vertically upwards in the medium, then the viscous force is acting downwards. So viscous force is almost equals to the frictional force in solids. Both are analogous to each other. Frictional force opposes the relative motion between the two solid substances. Like viscous force is also opposes the relative motion between the solid and fluid. So that viscous force is opposite to the relative motion of the body itself. So we have to see in which direction the object is moving. And in opposite to the direction, the force is applied, force is acting. Got it? So these are the basic knowledge regarding the forces which are involved in this experiment. First we know that formulas, then immediately we can apply that. And next, we must have a very good knowledge of free body diagram. So whenever there is a force involvement, there must be a vector involvement. So free body diagram, having the knowledge of free body diagram is must. Right. Now coming to the schematic diagram of I will write the diagram here. Coming to the diagram of the Millikan's ice drop experiment. A very small diagram. Give me a few minutes, I will draw it, get back to you. Now look at that diagram, a very schematic diagram, model diagram we say. So what are the parts involved in this diagram? So the first one is the atomizer, which consists of liquid, oil we say, whatever be the oil, it is different kinds of oils, okay? So the atomizer. With the help of the atomizer, so there is a like piston like thing, you can press it so that the liquid is sucked up and it moves through a narrow pipe. So here it is going to be sprinkle. So the liquid droplets are moved with high speed such that whenever they are passing through a narrow gap, because of the friction, the liquid drops acquires some charge. The liquid drops gets charge by friction. Charges can be induced or produced or generated by three ways. One is friction, another one is conduction, third one is induction. There are three kinds of processes. In 9th class or 10th class, where I am not sure about that, you have an example like if you take a comb, if you comb the dry hair with a new comb very rapidly and place the comb near where the paper clips, so there is always an aquatic force. So the comb acquires some charge because of the friction between the dry hair and the comb. So the charges are redistributed, that is the point. Likewise, here also because of the friction, the oil drops gets the charge. Now they are entering into the field. Now here the A and B are metal plates connected with the positive or negative terminal of the battery itself. We can change the polarity of A and B. There is no fixed one. Suppose if I am taking this one as the positive and this is going to be the negative, for example. So the field direction is vertically downwards. When it is a positively charged plate, it is negatively charged plate. The field is like this. Now the droplet is entering into the field. Then whenever it is moving, let it be the air is in the medium here. Air is the medium. So what are the forces experienced by that single droplet? He succeeded to maintain that, the Millikan succeeded to hold the charged particle for a particular instant of time. He is trying to hold the charged particle, which means it just freely falling, like a freely falling body it is moving. Because of the charge acquired by the droplet, suppose if the droplet acquires a negative charge or a positive charge, whatever it is, whatever be the charge it is acquired, we don't know that whether it is a positive charge or negative charge. For example, that droplet is getting the negative charge. Initially it is just freely falling body, so the gravitational force is acting on this. Since the droplet is moving in the medium of air, whatever it is, air or something medium, it is also experiences the buoyancy force. And it is also having the viscous force. So three forces are initially acting. Then what are the directions of the gravitational force, buoyancy force and viscous force? Gravitational force is acting trying to vertically downwards. Buoyancy force is acting vertically upwards. Since the particle movement is vertically downwards, the viscous force is acting vertically upwards. Now we are giving the field intensity such that initially it is just moving down. It is just moving down. So we are giving the charge to the plates positive and negative. What is the charge we are considering here? Negative charge. If I am giving the positive charge to the plate here, the negative charge, there is a repulsion between these two. So the velocity of the particle is going to be 0. The velocity of the particle is going to be 0. Not 0, sorry. Acceleration 0, which means the velocity is constant. And all of a sudden it is trying to move upwards. Now again he is trying to change the polarity itself. So likewise, at a particular instant of time, the net force experienced by the charged particle is 0. The net force experienced by the particle is 0, which means all these four forces are balanced with each other. Then we have to draw the free body diagram for that particular particle, and in that expression we are getting an equation, right? So F1 like F2, F2 different forces, and there is an equilibrium forces equations. There we are going to apply these values, and then we are going to find the value of the charged particle. Got it? Beautiful, right? So now we are having the different cases, such as if the charge acquires here is the positive charge. If the particle is moving vertically downwards, if the charge of the particle is positive, if it is moving vertically upwards. Here, the gravitational force and buoyancy forces, their direction does not change, they are fixed. So there is a direction, the change of the force here, whether it is the viscous force or the electrostatic force. We will come across this one in different cases. Case 1, case 2, case 3 like this. Different cases will have. Okay, right? We'll do one thing. I will let expressions all the forces equations here. Okay, right. Better. Right. See, forget to take this. So the droplet is going to be held at stationary. So when the light is allowed to fall on the droplet, when the light is falling on the droplet, it just reflected the light itself, right? Now we are observing that the stationary particle with the help of a telescope here. He is saying that, the Millikan is saying that this droplet looks like a star. It looks like a star. It just gives the sparkle, right? Beautiful. So the droplet is at rest, momentarily it is at rest. But now, let us write the equations, the force equations here, so that it is easy to substitute the values, forces. Okay. Gravitational force is mg, that is in terms of, right, okay, let it be in terms of density. So dvz, buoyancy force is d prime vz, and electric force is qe, and the viscous force is 6 pi eta or v. So here V has a special name known as terminal velocity. I think you heard the word terminal velocity in first year. Once the particle is attaining the terminal velocity, there is no change in the velocity. If velocity is constant, the acceleration is 0. If acceleration is 0, the force experienced by the particle is 0. That is the point. Or if I am saying that F net is 0, A net is 0, which means the velocity is constant. That velocity is known as the terminal velocity. Even though F net is 0, the particle may be in motion. That is the point here. F net is equal to 0 doesn't mean that the particle is at rest. It is in moving. It is moving with a constant velocity. Isn't it? The constant velocity simplifies that acceleration 0. Acceleration 0 means F net is 0. Now, see this one. So the case 1, first case. In the first case, assume that. So we have to draw the graph of that free body diagram. Right. Assume that the field is applied downwards. Here the field in the sense electric field. Field is applied downwards, and charge acquired by the particle is negative. Just like that. If the particle is getting a negative charge, so there is a force of, see, the field is applied vertically downwards, like this, downwards. So there is a force of attraction between the upper plate with the negatively charged particle. Now it starts moving upwards with the velocity VE. VE is the terminal velocity of the particle due to the electric field. VE is the terminal velocity of the particle due to electric field. Once the particle is getting the terminal velocity, acceleration 0, F net is 0. Now, draw the free body diagram for this particle. So, the first one. So, this is the particle we are assuming. The gravitational force is acting vertically downwards without any doubt. The buoyancy force is acting vertically upwards. We know that. Now, coming to the next, electrostatic force. Here the electrostatic force is a negatively charged particle, it is against the field direction. So this is the electrostatic force. Since the particle is moving vertically upwards, viscous force is acting vertically downwards. If you are having doubt, you can just rewind that video for 1 minute or 2 minutes. Fg and Fb, it is okay, no issues. Here the particle is getting the negative charge, electric force is acting vertically upwards since the field is downwards. Since the particle is moving vertically upwards, the viscous force acting vertically downwards. Now write the equations. Write the equations for the force. Fp plus Fe is equal to Fp plus Fz. Because the particle is with the terminal velocity, acceleration 0, F net 0 means the forces are well balanced, you see. The forces are well balanced. So, Fb plus Fe is equals to Fv plus Fz. By giving the values here, d prime Vz. Here V is the not velocity, volume. Careful, volume. Plus QE is equals to viscous force is 6 pi eta or VE. Here VE is the velocity, terminal velocity due to the electric field, plus dVz. Let it be, this is equation 1. Let it be the equation 1. Now, if the electric field is switched off, then what happens? The electric field is switched off. There is no electric field. So only the forces are gravitational force, buoyancy force and viscous force. Then what happens? If there is no electric force, the particle is trying to move vertically downwards. Something like a freely falling body. If electric field is switched off, then the particle or the oil drop move downwards. Now again write the expression, a free body diagram for that one. So in this case, the particle, the velocity, the gravitational force is vertically downwards, buoyancy force vertically upwards. Since the particle is moving downwards, viscous force is acting upwards. So Fv. Now it is moving with some velocity, terminal velocity again. The terminal velocity direction is like this because of the gravity. The terminal velocity due to gravity. Again, terminal velocity means constant velocity, that is acceleration 0, that is force 0. So I have to equate these forces. So Fb plus Fv is equals to Fz. What is Fp, Fz? Okay. So d prime Vz. Here V is the volume. Good. Next, 6 pi eta or Vz, where V is the terminal velocity of the particle due to gravity, is equals to dVc. Is it visible? Yes. Beautiful, right? Beautiful. Good. Well defined theory with well developed mathematics. Now we come across two equations. Good. Good. So let us do one thing. Equation 2 minus equation 1. What we are getting? If I am doing that like that, equation 2 minus equation 1, on left side that take equality, there is d prime Vz, here also d prime Vz. On the right side dVz, dVz. These two get cancelled each other, isn't it? Then 2 minus 1 gives. So on the left hand side I am having this 6 pi eta RVz minus, here it is the QE is equals to, on the right side, that so called dVz get cancelled and I am having only 6 pi eta V, 6 pi eta all, 6 pi eta all VE. From this, what I am expecting actually? The value of Q, right? So I am writing this one as Q is equals to, by taking the 6 pi eta all as common, 6 pi eta or Vz minus Ve whole by E. But I am not satisfied with this expression. I am not satisfied with this expression. because here to find the value of the charge acquired by the oil drop, I know the field intensity of the drop applied. I can estimate the Vc and Ve, where these two are the velocities. Velocity can be estimated like the distance traveled by the particle in a time interval t. So, the distance traveled by the particle in a time t gives the velocity. So, I am getting the values of Vc and Ve. 6 pi eta are constants. Whatever the value of r, how can I estimate the radius of the droplet? Is there any device which can measure that one? No. So, I need to use another equation or another thing to find the value of r. Now, look at the equation 2. So, from this, can I subject the r value? Can I find the value of r from the equation 2? Yes, I can. So, by bringing this d prime is into here and subject this r value. Substitute the value of r in equation 3. Good. Substitute the value of r in equation 3. Okay, good. From equation 2, pi eta or Vz is equals to, I am taking the Vz as common or Zv, whatever it is, Zv times of d minus d prime. From this we can say r is equals to Zv into d minus d prime by 6 pi eta Vz. This Vz indicates the terminal velocity due to the gravity. Z times V. V is the volume of the droplet. Am I right? Yes, volume of the droplet. Volume, if the droplet is acquiring the spherical ball like that, usually, due to the surface tension, every object is trying to occupy the less surface, right? Less area. So, volume, so that is 4 by 3 pi r cube. So that is Z d minus d prime by 6 pi eta Vz times of 4 by 3 pi r cube. This is equals to r. Now pi get cancelled. We can simplify this one and find the value of r. Substitute the value of r in equation 3. We are getting the charge. So make it pause for 5 seconds. Try to write that. Okay. So in the previous expression, here r is equal to something. By simplifying this one, we are getting the r is the root over 9 eta Vz by 2z into d minus d. Don't cancel this z and z. Ready 3. So this Vz is the terminal velocity due to the gravitational field. This is the acceleration due to gravity. Now, if the value of r is substituted in equation 3 and get simplified, then in this small expression, small equation, q is equal to 6 pi eta Ve plus Vz by capital E into something root over half. Power half. In this expression, I know each and every value here. Whether it is the terminal velocity due to electric field, terminal velocity due to gravitational field, field intensity, coefficient of viscosity, density of the material, density of the medium, and everything. If I am substituting all these values, the charge of electron is estimated like, so that the charge of electron is 1.6 into 10 power minus 19 coulombs. Right? This is the first and primary case. We are having two or three more cases that will be discussed in the next class. Okay? So you need to practice this derivative part. It's must. Okay? We'll meet later. Thank you. Bye.